The speaker is Professor Jae-Hoon Kwon at Seoul National University. He's going to talk about Q-deformed Howe duality for orthosymplectic Lie superalgebras.
Thank you for the introduction. So I would like to first thank the organizing committee for giving me the chance to give a talk here. So my talk today is based on one of my recent work with Jeong Bae. So I think I'm one of the speakers who is more related to the second keyword of this conference, the algebra. So today in this talk, I want to introduce a q-analogue or q-deformed version of a well-known classical result in representation theory. It's called the Howe duality. And in representation theory, duality often refers to a connection between two module categories of different algebras, which is given in terms of certain functors with good properties. So in case of Howe duality, actually it connects the representation of a classical Lie groups, their finite dimensional representation, and certain nice family finite dimensional or sometimes infinite dimensional representation of classical Lie algebras. Okay, so first I will briefly recall what Howe duality for classical groups are. And then I will introduce the notion of orthosymplectic Lie superalgebra, which is one of the important class of simple Lie superalgebra introduced by Katz. And then I will talk about the q-analogue of the orthosymplectic Lie superalgebra and its representation of the infinite dimensional representation in general, called the oscillator representation. Then with these materials, then I will introduce a q-deformed version of the Howe duality for the orthosymplectic Lie superalgebra, which makes a pair with the classical Lie groups. Okay. So let me start with the Howe duality for classical groups. Okay, so let me start with the vector space U, which is a tensor product of C to the M and C to the L. And then we know that the C to the M, just by left multiplication, it is a natural representation of GLM. And also C to the L is also a natural representation of GLL. So it is U is just a bimodule of this pair of two Lie algebras. Then now we take the exterior algebra generated by this vector space U. Then still we get a joint action or commuting action of these two Lie algebras. But the Howe duality of type A actually says that these two commuting actions of two Lie algebras are actually the centralized of each other. So that means, more precisely, when we consider the whole linear endomorphism of our exterior algebra, and then if we consider the subalgebra, which commutes with the action of GLM, then Howe duality of type A says that actually this subalgebra is generated by the another GLL actions on this space, and also vice versa. So sometimes it is called, we say that these two pairs satisfy the double centralizer property. Okay.
What do you mean by generated by GL actions?
So lambda of mu is the module of GLL. So that means that there is algebra homomorphism from the enveloping algebra of GLL into the endomorphism algebra with lambda of u. So generated means that the subalgebra is generated as an algebra by the image of the GLL action on this endomorphism space. Okay. So this is a non-trivial property. So once we have a double centralizer property, then we have the following decomposition of our exterior algebra as follows. Okay. So it is a direct sum of the tensor product of the finite dimensional irreducible representation of GLL and the multiplicity space W lambda. So here is the definition of W lambda. It's just a of lambda of U to the irreducible free lambda of GLM. And from the double centralizer, from the commuting action of these two algebras, this multiplicity space becomes naturally a GLM module. And then also from the double centralizer property, this actually becomes an irreducible representation. Okay. So partition. Yeah. So it's the well-known finite dimensional representation of the GLL, polynomial representation. Yeah, the parameterized partition whose lengths are less than or equal to L. And roughly speaking, the proof of double centralizer property is based on the first so-called the first fundamental theorem due to Weil, which appear in the classical invariant theory. Okay, so now actually one may extend this duality of type A to the other classical groups. So we still consider the same exterior algebra generated by U. So there is a joint action of GLM and GLL. And now we consider the action of the classical subgroup of GLL, say orthogonal group OL and symplectic group SPL. Then the Howe duality of classical groups says that there is an action of classical Lie algebras SO2M when G is OL, and SP2N when G is SPL, which extends the action of GLM, and also such that these actions commute with the action of this classical subgroup, and also satisfy the double centralizer property. So from the general theory of double centralizer property, we have the following multiplicity-free decomposition of our exterior algebra as a module over this pair of Lie algebra and Lie group. So here, V lambda G is the finite dimensional irreducible representation of G, parameterized by a certain subset of partition. And V upper bar lambda is the multiplicity space of this irreducible, but now it becomes an irreducible representation of G upper bar. Yes?
Take the role of exterior algebra here. Why exterior?
Okay, that's a nice question. Actually, there are analog of the symmetric algebra case as well. So there is a version where the duality happens on the symmetric algebra. So we still use the same vector space U, and now we consider the symmetric algebra generated by U. So it is an infinite dimensional algebra. But also still we have a joint action of GLM and the GLL. And actually they also satisfy the double centralizer property. And now we consider the action of the classical subgroup, say G, on this S of U. Then we also can say that so it is proved that there is an action of a classical Lie algebra G, say lower bar, SP2M when G is OL, and SO2M when G is SPL, which extends this action of type A and commutes with the action of G, and finally satisfy the double centralizer property. So now we have the following multiplicity-free decomposition S of U as a module over the pair of G lower bar and capital G. And also there is the same, so still we have the same finite dimensional irreducible representation of a classical group G, but now is multiplicity space in this symmetric algebra. It is an irreducible representation of SP2M and also 2M, which is realized as a multiplicity space of this irreducible component. But now the difference is that the difference with the previous slide is that this multiplicity space is now an infinite dimensional irreducible G lower bar module, so which is known as the oscillator representation. Okay.
I have a question.
Yes.
Where did the name oscillator module come from?
Well, I'm not quite sure I have a correct answer, but actually the action of the classical Lie algebra G lower bar on S of U comes from the action of the Weil algebra generated by U, which actually acts on S of U irreducibly. So this irreducible representation of SU over the Weil algebra is called oscillator representation as well. Actually, the action of the classical Lie algebra realized in terms of the Weil algebra, actually the differential operators acting on the symmetric algebra. So that's why I think it is called oscillator representation. But I'm not quite sure it is a quite correct answer. Okay. So combining, so I have introduced two dualities for the classical groups. Anyway, combining these two dualities for the pair of the G lower bar G and G upper bar of G, then we just have very elementary set theoretic correspondence between the representation of a classical Lie algebra of SP2M and also 2M, and also SO2M and SP2M, where both of them are realized as the multiplicity space of the same irreducible representation of the classical group appearing in the Howe duality of exterior and symmetric algebras. Okay. So actually these set theoretic, some elementary correspondence can be explained more directly in terms of the duality which is related to the superalgebra. So more precisely, one may explain this correspondence by emerging two dualities on the symmetric and exterior algebra into a single duality using the simple Lie superalgebra. So this is a duality which I'm going to talk about. So let me explain a little bit details of this notation. So we start with the superspace C to the Mn. This is nothing but a integrated space where the even part is the C to the M and other part is the C to the N. Okay. Then we consider the L copy of this superspace and then consider the supersymmetric algebra generated by this one. So supersymmetric is nothing but we just allow the commuting relations on the other even part, and then to allow the anti-commuting relations on the other part. Okay. Then there is a theorem by Shunjun Chang and Ribin Sang, where there is a commuting action of the simple Lie superalgebra called orthosymplectic, and the action of the classical group of GLL. Still, we use the same one, OL, SP2L. So they are commuting with each other, and also they satisfy the double centralizer property. So I will explain in a later slide what this simple Lie superalgebra is. More precise definition I will give in a couple of minutes. And why this duality explains both two dualities on exterior and symmetric algebra. So here is a duality on this pair of Lie super and classical group. So from the double centralizer property, we have a multiplicity free decomposition where tensor product of irreducible V lambda G and is multiplicity space. I haven't defined it yet, but anyway, first, if we take M to be 0, then this space becomes C to the L times C to the N, and C to the N is just the odd space. So the supersymmetric algebra generated by this case is nothing but the exterior algebra. And also, if we special M to be 0, then SPO2M to N just goes to SOM, SO2M. So this recovers the duality on exterior algebra, which I interested in the very beginning. And also when, in case of this pair, when G is sp2L, we also recover this duality. And also if we take n to be 0, then now we only have the space of even degree. So the whole supersymmetric algebra is nothing but the symmetric algebra generated by this space. So also we can recover the duality on this symmetric algebra. Okay, so let me briefly review what the definition of OSB, and also recall some very basic property of this Lie superalgebra for those who are not familiar with this notion. Okay. So we start with the superspace, it's just a Z-integrated space. And then we consider the linear endomorphism of V. Then from the Z-grading of V, actually the endomorphism of V becomes a Z-graded space. Then we can define the supercommutator using the degree of the endomorphism space. So with this, the supercommutator, the GLV, it becomes a Lie superalgebra, which we call or denote, which we call the general linear Lie super, and denoted with GLV with the same notation as in the case of simple Lie algebra. Okay, so now we consider another family of simple Lie superalgebra as a subalgebra of GLV. So, as in the case of a simple Lie algebra, we start with a certain non-degenerate bilinear form to define the classical time. So we consider the even non-degenerate supersymmetric bilinear form, which is a very long terminology. But anyway, this is equivalently means that when we restrict the B to the even subspace, it is symmetric. And if we restrict it to outer space, it is symmetric. And also, it is orthogonal on the pair of spaces with a different parity. Okay, so then we defined OSB of V to be the subalgebra of GLV, which preserves this bilinear form. So it also becomes a Z-graded space, actually Z-graded superalgebra, whose homogeneous components are given by this form. Okay. So this one is this is called the orthosymplectic superalgebra, and it forms a family of simple Lie superalgebra according to the CAST classification. So in particular, when our superspace is a standard one, C to the L to M, then we simply denote the corresponding OSP to be by OSP L bar to M. And also from the definition in the previous slide, it's not difficult to see that actually the even part of this Lie superalgebra, so which is a Lie algebra, is a direct sum of two simple Lie algebra, SOL and SP2M. And also we can define the similar notion with the even non-degenerate super skew-symmetric bilinear form, say B prime, then the corresponding Lie superalgebra, we denote it by SP of V, but it's basically odd part is just not Lie superalgebra, it's a module over the even part. Okay. But anyway, so SPOV is also essentially also symplectic Lie superalgebra, but for convenience, we use this notation. Okay. So let me give a little more details about the structure of OSP. So let us consider OSP 2M to N. So it is a subalgebra with GL 2M to N. So here we fix the linear order on the set of indices of the matrices of 2M plus 2M square matrices, where the index for the even parities comes first. Okay. Then we consider the non-degenerate supersymmetric bilinear form given by this formula, then we denote this corresponding OSP to be the 2n bar to n. Okay. So it is a simple Lie superalgebra, as I mentioned just before. And also, like the semisimple Lie algebra, it has a triangular decomposition. So with respect to the action of a Cartan, the other components has a root space decomposition. So their combinatorics also play a very important role in the representation theory of simple Lie superalgebra. So let me describe what the roots are in this case. So to describe the root, let us consider the standard dual basis of the Cartan subalgebra of H. Actually, H is the Cartan of the even part of this one. So it is the Cartan subalgebra of SO2L and SP2M. Okay. Then there is a killing form on OSP. So it induces a non-orthosymmetric bilinear form on its dual. So the induced bilinear form is given by this formula. Then with respect to this dual basis, the set of positive roots is given by the following form. So it is a disjoint union of the set of positive even roots and set of positive odd roots where the parities are depending on the corresponding root vectors in Lie algebra, Lie superalgebra. So for the even part, so this is a disjoint union of two sets. And if you are familiar with the root system, then you can easily see that actually the first set is nothing but the positive roots of type A. It's actually GLM and GLN. And the other set is and also you can see that consists of the positive roots of SO2M and SP2M, which are not of type A. And also, in super case, we have extra root, say odd roots, given by the following form. And from our induced bilinear form on the dual space, there is an interesting thing happens that some roots are their norm with respect to this bilinear form, their norm is 0. So we call these positive roots isotropic. Okay. So in this case, we can take a subset of positive roots, which is called the set of simple roots or fundamental system, which corresponds to generators of our simple Lie superalgebra. And with respect to our bilinear form dual space, the thinking diagram looks like this. So it is almost the same as the thinking diagram of type D, but there is an isotropic simple root in the middle. So that's the difference of the usual simple Lie algebra. And also similarly, we have a description of positive roots and fundamental system so that the associated thinking diagram looks like this. Okay, so that's a very basic. Super. Okay, so, and finally, I want to remark that actually this was also mentioned in the previous talk, and that the representation theory of a simple Lie super, not only OSP, is not parallel to that of the semisimple Lie algebra. So for example, one of the crucial differences is that finite dimensional representations are not semisimple in general. That's the crucial difference. So that's why many people in representation theory have been interested in working on the representation of Lie superalgebra for the last couple of decades. Okay. Okay, so let me come back to duality. So, okay, so our goal is the goal of this talk is to give a q-analogue of the following duality on the supersymmetric algebra generated by these spaces, where the pairs are SPO2M2N and OL, and OSP2M2N and SP2L. So to get a q-analogue of this picture, we have to quantize the action of the First, the orthosymplectic superalgebra, and then we have to quantize the action of the classical groups. Okay. And also, I would like to remark that when non-super case, so equivalent to when m equals 0 or n equals 0, the Q-deformed version of the Howe duality of classical duality, classical groups have been already obtained by Sartori and Tugendhauer. And is one of our speakers, I think. And one important observation in their work is that the action of the classical group or their Lie algebra is not replaced by the Drinfeld-Jimbo's quanta group, the most popular one. But instead, it should be replaced by the action of the another quantized enveloping algebra of the associated Lie algebra called the iquantum group. But anyway, our goal is to generalize this work by the Sartori and Tugendhauer to the case of OSB. And also, as far as I understand, as I know that actually this kind of generalization is not quite straightforward from their work. Okay. Q? Yes, there's a Q. Sorry?
What is it? iQuantum group?
iQuantum group. It's I will introduce in this couple of minutes. I is not a complex number. Okay, so the most important, most well-known quantized enveloping algebra for the orthosymplectic superalgebra is the one introduced by the Yamane quite long ago. But instead of using Yamane's quantum superalgebra, I will use, we used another quantized enveloping algebra of the OSP. Our notation is UC and UD, and also it depends on a certain sequence of the 0, 1. Okay. So that quantized enveloping algebra was introduced by, more recently compared to Yamane, introduced by Kuniba, Okado, Sergeev, where they called it the generalized quantum group. And actually, they introduced this Q version in their study of the three-dimensional Yang-Baxter equation or tetrahedral equation. And also, I would like to mention that this version of the enveloping algebra is slightly different from the Yamane's quantum group. But also, I'd like to remark that basically the category of representation of these two algebras are the equivalent, because we can show that after a slight extension of adding some generators, there is isomorphism between the generalized quantum group Kuniba, Okada, Sergeev and the Yamane's quantum group. Okay, but this is not just a matter of a convention. The reason why we use the generalized quantum group is that the co-multiplication is more compatible with in this duality setting. More precisely, the isomorphism I just mentioned between the generalized quantum group and Yamane's quantum group is not actually a Hopf algebra isomorphism. So the tensor structure of the generalized quantum group is slightly different from the Yamane's version. So there is a non-trivial difference. I think it is one of the important points in our work. Okay. So anyway, in particular, the generalized quantum group also recovers the usual Drinfeld quantum group when the parameter is homogeneous. So for example, when epsilon I is all 0, then it just ux just gives the uxn, the Drinfeld-Jimbo quantum group of type xn, x is C or D. And also when epsilon i's are all 1s, then it still gives the same Drinfeld-Jimbo quantum group of the same type. But the one important fact is that now the quantum parameter is not q, it should be replaced by minus q to the minus 1. And also when the parameter is a standard one, that means the 0 and 1s are not shuffled, then it can be viewed as a natural q-analogue of our enveloping algebra of SPO2M to N with respect to standard Borel. And also UD can be viewed as a q-analogue of the U of SP2n to n with respect to standard Borel. Okay, so here the sequence epsilon, actually we consider all the arbitrary sequence of the 0 and 1s. And conceptually, this sequence represents the type of Borel subalgebra of our simple Lie superalgebra. And also, the one crucial difference between the semisimple and simple Lie superalgebra is that on the side of simple Lie superalgebra, the Borel subalgebra not actually conjugate to each other under the action of the Y group of the even part. Okay, so anyway, epsilon denotes the fundamental system or the corresponding Borel, which are not conjugate to each other. And also I have mentioned that this algebra is a Hopf algebra with a co-multiplication. So for example, in case of Chevalier generators, it's given by the following formula. The reason why I write down this formula is that if you are familiar with the usual Dirichlet-Gimbel quantum group, then the co-multiplication formula is exactly the same as the usual Dirichlet-Gimbel quantum group. But if you are using the Yamane's quantum superalgebra, then in that case, the co-multiplication, actually we have to consider additional linear operator. You have to put those operator inside this co-multiplication formula, where those operator actually acts on the superspace by diagonally plus 1 or minus 1, depending on the parity of the superspace. Oh, yeah, this is the another generators of the, which, so EI, FI, and KI plus minus 1 is the generator of the UQSL2. Yeah. So the tensor structure of generalized quantum group is different from, non-trivially different from the usual quantum superalgebra. And it is more compatible with that of the usual quantum group. Okay, so now let us consider the q-analogue of the duality. The Howe duality for the orthosymplectic Lie super. So first we observed that the action of the orthosymplectic superalgebra on the supersymmetric algebra. And then we first observed that actually this module structure can be factorized into the L tensor power of the small supersymmetric algebra generated by the C to the Mn or 2 copy of it. So as a first step, we construct a q-analogue of the action of UXE on the q-analogue of these two supersymmetric algebra, which we denote by the W and W square. Just a formal notation, the q-analogue of this module. So I will introduce the notation. Okay. So actually, we define the action of the Chevalier generators very explicitly, and they are not very complicated. But I'm not going to show all the formulas. But anyway, here is an example. So in case of type D, let W be the vector space whose bases are parameterized by the n plus n tuple of non-negative integers, where each component is non-negative integers or it's a binary, depending on the parity of the index. Okay. So as a vector space, it is isomorphic to the supersymmetric algebra as a vector space. So for example, the action of the Chevalier generators corresponding to the simple root, which correspond to alpha 0 in the thinking diagram of type D, or the leftmost one in case of type C. These formulas are given by the following forms. So in case of W, it's just removing or adding the ones on the first two components. And also in case of W square, which is as a vector space, the 2 tensor power of W. we define the action in this by these formulas. It also acts just by removing or adding the ones in the first two components. But also I should mention that these actions are not induced from the W by co-multiplication. It's an independent action. Okay, so for example, when epsilon is standard or homogeneous, then our action gives the following q-analogue of the action. So for example, in this case, UD acting on W is the q-analogue of the SPO action on this supersymmetric algebra. And if we take n to be 0, then it recovers the q-analogue of the SO2m on the exterior algebra, which is known as a spin representation. Yes. Yeah. Because the linear basis has the same parameterization. And also on the side of C, we have a q-analogue of SPO action on this space. And one more important technical assumption is that m should not be 0. But anyway, if we take n to be 0, then we recover this q-analogue of the oscillator representation of type C. And on W square, we also have the following analog of the OSB action, and also here. And except the last one, the other first three actions, the q-analog actions are based on the previous by other people. Okay. Sorry? A Q, okay. Oh, the previous, go back. There is a Q. Yeah.
But this weight exterior depends on Q, right?
Yes. Yes. Actually, we do not consider the multiplication of exterior algebra. We just consider the action of the OSB or its quantum version. Okay. So I have a couple of remarks. So the actions, which I actually didn't give the formula for the actions, but just gave an example. But anyway, the action of our generalized quantum group of W square, also including W, are obtained by rather brute force way, but somehow it's taking suitable q-analog of the original simple Lie algebra of a classical type. It's the action on the symmetric and the exterior algebra. But our motivation is by looking at the crystal structure of finite fundamental representation of the UQ, SP2L, and SOL. And the second remark is the one I already mentioned. So anyway, now we have a q-analog of the action of the generalized quantum group of a smaller supersymmetric algebra. So now from the Hopf algebra structure, we have two kinds of representation of generalized quantum group, L tensor power W and L tensor power W squared. So as a first step to establish the q-analog of the duality, we first show that these L tensor power of our representations are actually semisimple. These are done by taking a classical limit of our representation. And also there is another way to prove semisimplicity by proving the existence of some kind of a nice invariant bilinear form called a polarization. But anyway, we first show that they are semisimple. And next we show that, so since they are semisimple over ux epsilon, so we have to characterize the irreducible components appearing in this space. And we show that any irreducible factor appearing here is also a highest weight module, say curly V lambda, which can be viewed as a natural q-analogue of the oscillator representation V lambda appearing in the Howe duality of orthosymplectic superalgebra. And also by comparing the character of our space, whole space, we show that the L tensor power W, for example, is a direct sum of curly V lambda, where its multiplicity is equal to the dimension of the irreducible representation of OL corresponding to the partition lambda. And similarly, in case of W square, the multiplicity is equal to the dimension of the irreducible representation of symplectic group. Okay, so now let's consider the Q-deformed duality. So for convenience, let us denote the W and W square by just F. Then summarizing what we have just talked about, the F tensor L is a semisimple module over the generalized quantum group and with the irreducible component of V lambda. So now we can think of it as a multiplicity space, sum of V lambda into F tensor L. And now we want to, so to have another action commuting with the ux epsilon, we have to quantize the action of the classical group, SPL and SP2L and OL. And also I have mentioned, in we have to quantize the action of this classical group acting on this multiplicity space semi-simply. So we start from, as in the classical picture, we start with the duality of type A first. So we consider this space, Fock space, and then it is not difficult to see that there is a joint action of the Drinfeld-Jimbo quantum group of type A and another quantum group of type A, which is a subalgebra of our generalized quantum group. So it is a subalgebra type A, roughly speaking, corresponding to the subdiagram of the thinking diagram of the whole one by removing the leftmost one or alpha 0. Okay. So it is a quantized enveloping algebra of the general linearly superalgebra. So then we can naturally define, we can easily check that these two actions commute and they satisfy the double centralizer property. Okay. So we start from this type of type A duality. So, okay, so now we have to, so, and also, okay, and also, okay, so this is the picture we want to think about, and we already quantized the action of OSP inside, on the left-hand side, by extending the action of type A. Okay. So now we have to consider the action on the right-hand side. But as I already mentioned, that there is no natural q-analogue, the action of OL or SP2L, or it's a Lie algebra, given in terms of the Drinfeld-Jimbo quantum group, UQ-SOL and SP2L. Because there is no obvious embedding of this quantum group into the quantum group of UQGLL or UQGL2. So as observed in the previous work by Sartori and Tubenhauer, we have to consider the I quantum group. So this is nothing but this is a kind of subalgebra of the Drinfeld-Jimbo quantum group of type A, generated by certain generators, which I'm going to explain in the next slide. But anyway, it is a subalgebra, actually quite a subalgebra. And it can be viewed as a q-analogue of the symmetric pair of the pair of Lie algebra of SL, SOL, SL12, and SP12. Then what is a symmetric pair? So roughly speaking, a symmetric pair is a pair of a simple Lie algebra and it's a subalgebra, say K, which is given by the fixed point subalgebra with respect to a involution of G. This kind of pair naturally appears in the classification of symmetric spaces in geometry and also appears in the classification of real simple Lie algebras. So our subalgebra, say UI of K, which is a subalgebra of the Drinfeld-Jumbo quantum group type A, is another q-analogue of the enveloping algebra of U of K. And it was introduced by Letzer already quite long ago. And now, yeah, I think so. It is related to. So now it is also often called the iquantum group. And also UIK is not a Hopf algebra, but a co-ideal subalgebra. So that means that if we apply the co-multiplication of the quantum group GL, then the image of our iquantum group lies not inside of the 2 tensor power V, but inside the tensor product of UIK and the UQ of G, or the tensor product of in the other direction, depending on whether it is a left or right co-ideal. But anyway, recently, for the last couple of decades, it was found that the UIK, the I-quantum group has also a very rich structure parallel to the usual theory of the quantum group. Many studies have been done so far. Okay, so I'm not going to give a full definition of I-quantum group, but let me briefly recall what the definitions are in case of our symmetric pairs. Okay, so in case of type GK, when GKs are SL and SOL, which is also called the type A1 of Satake diagram. In this case, the involution is nothing but the Chevalier involution, which exchanges the Chevalier generates EI and FI. Okay. So in this case, UI of SOL is the algebra of this one, generated by these generators, BI, given by this following formula. And also in case of type A2, the pair is SL12 and SP12. In this case, the involution is given by the composition of 2 automorphisms. One is the Chevalier involution, and the other is the automorphism associated to the following Weiergroup elements, product of S1, S3, and S12 minus 1, which are the simple reflections corresponding to the simple roots, corresponding to these white vertices of the thinking diagram of the type of SL12. Okay. Then our I-quantum group, or the UI SP12, is the subalgebra generated by these elements. And here, PW dot is now the Lustig braided symmetry associated to this Weiergroup elements. Okay. Okay, so now we are ready to state our main theorem. So first, we show that. So now we have a 2 action of the Q-deformed version of the Lie super and the actual classical Lie or is Lie algebra. Anyway, so we show that these 2 actions are commute with each other. So the proof is quite lengthy. It's just elementary, but we need quite lengthy. We just checked by brute force. We don't know yet what some kind of conceptual or novel proof of it. Okay. Anyway, we showed that these 2 actions commute, and then so that the decomposition of our Fock space, the L tensor power of F, is a direct sum of the tensor product of the UV lambda and the multiplicity space now as a module of our iquantum group. So finally, to establish the semisimple decomposition of our Fock space, we proved that this multiplicity space as a UIK module is semisimple. So it is not actually irreducible, but in most cases it is irreducible. For example, if K is symplectic or if K is orthogonal, together with some technical condition on the L or the partition. Otherwise, it is sum of two irreducible. But still, it coincides with the usual decomposition of the finite dimensional representation of the classical group into the decomposition as a module of a Lie algebra. And moreover, we show that by taking the classical limit, so that means by taking the limit at q equals 1, we show that it recovers the Howe duality for orthosymplectic Lie superalgebra. So so this actually gives the q-analogue of the Howe duality for orthosymplectic Lie superalgebra. Okay, so let me end my talk with a couple of remarks. So the proof of the second part of the theory, which is about the semisimplicity of wave space, multiplicity space, which is a representation of the iquantum group. It's not, at least as far as I understand it, it's not obvious. But anyway, we use the theory of the classical weight module recently introduced by Watanabe. Okay, and the other comments are some future or the other related topics. So the second one is the combinatorics of this Howe duality. So I think it would be interesting to study the combinatorics of this duality picture at q equals 0. For example, in case of type A duality, the combinatorics of q equals 0 corresponds to so-called the Robinson-Schoenstatt correspondence, which are very famous for in the algebraic combinatorics. Okay. But anyway, it would be very interesting, at least to me, the direction of this duality. And this is an ongoing project joint with Watanabe. And also there is another interesting work, which is another work joint with the Shimyeon Lee in Kiasi here and Okado, where we consider a certain category of quantum affine, also symplectic superalgebra, where when restricted to a classical component, it is semisimple, and its irreducible components are the q-analogue or the oscillator representation, which appears in this picture. Then actually we show that in this category, that we constructed a very large family of irreducible representation of the quantum affine, also symplectic superalgebra. And what also interesting is that somehow this category behaves very similarly to the case of the category of finite dimensional representation of quantum user affine algebra. And actually we consider certain concrete functors connecting those two categories. And one of our conjecture is that after a certain limit, we hope it gives a kind of equivalence. Okay, so that's also my talk, and let me stop here.